A 75-kilogram bungee jumper is about to step off of a platform high above a raging river and plummet downward. The elastic bungee cord has an effective spring constant of 50 newtons per meter and is initially slack, although it begins to stretch the moment the bungee jumper steps off of the platform. In this problem, we can treat the bungee cord as a spring as long as it is being stretched. It does not make sense to treat the bungee cord as a spring being compressed, but if it's being stretched, we can treat it as a spring, and K is equal to 50 newtons per meter. It begins to stretch the moment the jumper steps off of the platform, and the mass of the jumper is 75 kilograms. We want to know how far the bungee jumper falls. So event 1 is when the jumper steps off the platform. Event 2 is at the lowest point. Let's say that at the lowest point, the height is equal to 0. So I am looking here for H1. My work energy conservation law, including elastic potential energy, says 1/2 mv initial, which is the initial kinetic energy, plus 1/2 ks squared, which is the initial elastic potential energy, plus mgh1, which is the initial gravitational potential energy, plus the work done by forces other than the force of the spring and the force of gravity, is equal to final kinetic energy plus final elastic potential energy plus final gravitational potential energy. So let's look at the forces that are acting on the jumper. So we have the force of gravity acting downwards. We have the force of the spring acting upwards. The magnitude of the force of the spring is K times S. And because the spring or the bungee cord is being stretched, K times S is going to be positive. So I only have those two forces acting on the jumper, so the work done by forces other than gravity is 0. The jumper is starting at rest. The cord is initially unstretched, so my initial energy is just mgh1. I have afterwards elastic potential energy, but no gravitational potential energy, and at the lowest point, this is a turning point. If there was still velocity going downwards, it would not be the lowest point because the bungee jumper would still be moving downwards. And if we had velocity acting upwards, the bungee jumper would have come from a lower position. So at the lowest point, the velocity is 0. So from my work energy relationship, I have mgh1 is equal to 1/2 ks2 squared. So everything else here in my relationship is 0. So I could now go ahead and solve, but I don't know what S2 is. Actually, I do know what S2 is because S1 was equal to 0 because this bungee cord began to stretch the moment the jumper stepped off of the platform. This distance here is S2, and this distance is the same as H1. So I can say this is equal to 1/2 kh1 squared. Now I want to solve for H1. I have H1 on one side of the equation and H1 squared on the other side of the equation, so I can cancel one of those. And then solving for H1, I have 2 times m times g divided by k. The mass is 75 and k is 50. This gives me 29.4 meters. In part B, I want to know the maximum speed of the bungee cord. Event 1 is going to be the moment that the jumper steps off the platform. Event 2 for part B is not the same as event 2 for part A. Event 2 in part B is going to be at the maximum speed. At the lowest point, the speed was equal to 0. I need to know something about what happens at the maximum speed. I have the same forces that I had before. I have Ks acting upwards. I have mg acting downwards. At the maximum speed, the acceleration must be equal to 0. If you were still speeding up, then the speed would not be at its max because it was still be increasing. If you were slowing down, the speed would not be at its max because it would have been at its max at some earlier point. So at the maximum speed, the acceleration is equal to 0. If the acceleration is equal to 0, Ks must be equal to mg. Because event 1 is the same as what event 1 was in part A, on the left-hand side of the equation for my work-energy relationship, I just have gravitational potential energy. But now I'm going to draw a new picture, and I'm going to say we haven't fallen quite so far as we did back here, but I'm going to make this new height 0, so h1 is not going to be the same as what it was up here. And this distance is s2, so not the same distance that it was up here, it's a smaller distance, but I'm still going to use the current height of the person for the height 0. So if I go back to my work-energy relationship, mgh is going to be equal to 0 because I said it was. And then I have kinetic energy, so this is 1/2 m v2 squared, and I'm looking for v2, and I have 1/2 k s2 squared also, but remember this is not the same s2 that we had previously. I have too many unknowns in this relationship to be able to solve it the way it is now, but I know that ks2 is equal to m times g, therefore s2 is equal to mg divided by k. So I can put that in over here. So I have mg h1 is equal to 1/2 mv2 squared plus 1/2 times k times s2, which is mg divided by k squared, and then I can solve this for v2. So this is mgh1, 1/2 mv2 squared plus 1/2 k over k squared, leaves me with a k in the denominator, and this is mg squared. Now solving for v2, let's do this first. So this is mgh1 minus 1/2 mg squared divided by k, then divide by the mass and multiply by 2 and take the square root. Multiply by 2, divide by the mass, take the square root. I can simplify this a little bit. So I have 2 times gh1 multiplying by 2 and dividing by the mass. Multiplying by 2 gets rid of the 1/2 here. Dividing by the mass gets rid of one of those m's. And I can plug numbers in here in order to find v2. I could if I knew what h1 was. I do know h1 is equal to s2. I know s2 is equal to mg over k, so I have to put that in also. So that gives me v2 is equal to the square root of 2 times g. h1 is equal to s2, which is equal to g over k minus mg squared over k, and that is the square root of 2mg squared divided by k minus mg squared divided by k, which is the square root of mg squared divided by k. So now we can plug numbers in, and you should get for this 12 meters per second. You can check to make sure that that works out. Notice here that our answer did depend on the mass, and that was true in part A also.